Boltzmann constant.
The Boltzmann constant, named after Ludwig Boltzmann, is a physical constant relating energy at the individual particle level with temperature. It is the gas constant divided by the Avogadro constant Na. It has the same dimension, energy divided by temperature, as entropy. The accepted value in SI units is 1.38064888, 13, x 10. 23 joules per carat.
Bridge from macroscopic to microscopic physics.
Boltzmann's constant, Kb, is a bridge between macroscopic and microscopic physics. Macroscopically, the ideal gas law states that, for an ideal gas, the product of pressure P and volume V is proportional to the product of amount of substance N, in moles, and absolute temperature T. Where R is the gas constant, 8.3144621, 75, Jk. 1 mole. 1. Introducing the Boltzmann constant transforms the ideal gas law into an alternative form, where N is the number of molecules of gas. For N equals 1 mole, N is equal to the number of particles in 1 mole, Avogadro's number. The left-hand side of the equation is a macroscopic amount of pressure volume energy representing the state of the bulk gas. The right-hand side divides this energy into N units, one for each gas particle, each of which has an average kinetic energy equal to kBt.
Role in the equipartition of energy.
Given a thermodynamic system at an absolute temperature T, the thermal energy carried by each microscopic degree of freedom in the system is on the order of magnitude of kBt/2, i.e., about 2.07 x 10. 21 J, or 0.013 eV, at room temperature.
Application to simple gas thermodynamics.
In classical statistical mechanics, this average is predicted to hold exactly for homogeneous ideal gases. Monatomic ideal gases possess 3 degrees of freedom per atom, corresponding to the 3 spatial directions, which means a thermal energy of 1.5 kBt per atom, in the general case, dkBt/2, where d is the number of spatial dimensions. This corresponds very well with experimental data. The thermal energy can be used to calculate the root mean square speed of the atoms, which is inversely proportional to the square root of the atomic mass. The root mean square speeds found at room temperature accurately reflect this, ranging from 1370 meters per second for helium, down to 240 meters per second for xenon. Kinetic theory gives the average pressure P for an ideal gas as substituting that the average translational kinetic energy is gives. So the ideal gas equation is regained. The ideal gas equation is also obeyed closely by molecular gases. But the form for the heat capacity is more complicated, because the molecules possess additional internal degrees of freedom, as well as the 3 degrees of freedom for movement of the molecule as a whole. Diatomic gases, for example, possess a total of 6 degrees of simple freedom per molecule that are related to atomic motion, 3 translational, 2 rotational, and 1 vibrational. At lower temperatures, not all these degrees of freedom may fully participate in the gas heat capacity, due to quantum mechanical limits on the availability of excited states, at the thermal energy available.
Role in Boltzmann factors.
More generally, systems in equilibrium at temperature T have probability P of occupying a state I with energy E weighted by the corresponding Boltzmann factor, where Z is the partition function. Again, it is the energy-like quantity Kb which takes central importance. Consequences of this include, in addition to the results for ideal gases above, the Annius equation in chemical kinetics.
Role in the statistical definition of entropy.
In statistical mechanics, the entropy S of an isolated system at thermodynamic equilibrium is defined as the natural logarithm of W, the number of distinct microscopic states available to the system given the macroscopic constraints, such as a fixed total energy E. This equation, which relates the microscopic details, or microstates, of the system, via W, to its macroscopic state, via the entropy S, is the central idea of statistical mechanics. Such is its importance that it is inscribed on Boltzmann's tombstone. The constant of proportionality Kb serves to make the statistical mechanical entropy equal to the classical thermodynamic entropy of Clausius. One could choose instead a rescaled dimensionless entropy in microscopic terms such that this is a rather more natural form. And this rescaled entropy exactly corresponds to Shannon's subsequent information entropy. The characteristic energy kBT is thus the heat required to increase the rescaled entropy by 1 nat.
Role in semiconductor physics, the thermal voltage.
In semiconductors, the relationship between the flow of electrical current and the electrostatic potential across a p-n junction depends on a characteristic voltage called the thermal voltage, denoted Vt. The thermal voltage depends on absolute temperature T as where Q is the magnitude of the electrical charge on the electron with a value 1.602 176 565, 35, x 10. 19 C and K is the Boltzmann's constant, 1.38064888, 13, x 10. 23 joules per carat. In electron volts, the Boltzmann constant is 8.6173324, 78, x 10. 5 eVK, making it easy to calculate that at room temperature 300 K, the value of the thermal voltage is approximately 25.85 millivolts. 26 megavolts. The thermal voltage is also important in plasmas and electrolyte solutions. In both cases it provides a measure of how much the spatial distribution of electrons or ions is affected by a boundary held at a fixed voltage.
History.
Although Boltzmann first linked entropy and probability in 1877, it seems the relation was never expressed with a specific constant until Max Planck first introduced Kb, and gave an accurate value for it, 1.346 x 10. 23 joules per carat, about 2.5% lower than today's figure, in his derivation of the law of black body radiation in 1900 to 1901. Before 1900, equations involving Boltzmann factors were not written using the energies per molecule and the Boltzmann constant, but rather using a form of the gas constant R, and macroscopic energies for macroscopic quantities of the substance. The iconic terse form of the equation S equals Kb log W on Boltzmann's tombstone is in fact due to Planck, not Boltzmann. Planck actually introduced it in the same work as his H. As Planck wrote in his Nobel Prize lecture in 1920. This peculiar state of affairs can be understood by reference to one of the great scientific debates of the time. There was considerable disagreement in the second half of the 19th century as to whether atoms and molecules were real, or whether they were simply a heuristic, a useful tool for solving problems. Nor was there agreement as to whether chemical molecules, as measured by atomic weights, were the same as physical molecules, as measured by kinetic theory. To continue the quotation from Planck's 1920 lecture. In 2013 the UK National Physical Laboratory used microwave and acoustic resonance measurements to determine the speed of sound of a monatomic gas in a triaxial ellipsoid chamber to determine a more accurate value for the constant as a part of the revision of the International System of Units. The new value was calculated as 1.38065156, 98, x 10. 23 Jk. 1 and is expected to be accepted by the International System of Units following a review.
Value in different units.
Since Kb is a physical constant of proportionality between temperature and energy, its numerical value depends on the choice of units for energy and temperature. The small numerical value of the Boltzmann constant in SI units reflects the small energy in joule required to increase a particle's energy by raising the temperature by 1 Kelvin. 1 DEGC is defined to be the same as 1 K. The characteristic energy Kb is a term encountered in many physical relationships.
Planck units.
The Boltzmann constant provides a mapping from this characteristic microscopic energy E to the macroscopic temperature scale T equals EkB. In physics research, another definition is often encountered in setting Kb to unity, resulting in the Planck units or natural units for temperature and energy. In this context, temperature is measured effectively in units of energy and the Boltzmann constant is not explicitly needed. This simplifies many physical relationships and makes the definition of thermodynamic entropy coincide with that of information entropy, where pi is the probability of each microstate. The value chosen for a unit of the Planck temperature is that corresponding to the energy of the Planck mass, or 1.416833.85 x 1032 K.
Boltzmann constant.
The Boltzmann constant, named after Ludwig Boltzmann, is a physical constant relating energy at the individual particle level with temperature. It is the gas constant divided by the Avogadro constant Na. It has the same dimension, energy divided by temperature, as entropy. Macroscopically, the ideal gas law states that, for an ideal gas, the product of pressure P and volume V is proportional to the product of amount of substance N, in moles, and absolute temperature T. Where R is the gas constant, 8.3144621, 75, Jk. 1 mole representing the state of the bulk gas. The right-hand side divides this energy into N units, one for each gas particle, each of which has an average kinetic energy equal to kBt.
Role in the equipartition of energy.
Given a thermodynamic system at an absolute temperature T, the thermal energy carried by each 1. Introducing the Boltzmann constant transforms the ideal gas law into an alternative form, where N is the number of molecules of gas. For N equals 1 mole, N is equal to the number of particles in 1 mole, Avogadro's number. The left-hand side of the equation is a macroscopic amount of pressure volume energy entropy. The accepted value in SI units is 1.38064888, 13, x 10. 23 joules per carat.
Bridge from macroscopic to microscopic physics.
Boltzmann's constant, Kb, is a bridge between macroscopic and microscopic physics.